What happens if we want to test a mean? Well, basically, it's going to be the same process. There's going to be a 4-step process. What are we going to do? Are we allowed to do it? Do it. What the heck does it mean? Okay. So, what are the conditions for testing a mean? Well, they're the same as they were for the confidence intervals. Is it random? They tell us or not. 10% condition. Is the population at least 10 times the size of the sample? How do we know if it's normal? Well, if n is greater than 30, by the central limit theorem, it's normal. If they tell us the population is normal, then it's normal. If n is less than 30 and we don't know about the population, we're going to make a box plot or a histogram. And if there's no strong skewness or outliers, cool, we can move on. Okay. Now, if it's a conditions for, or we're doing a significance test for a mean, it's going to be a little bit different than it was for a proportion, obviously, because how do we calculate X bar? Much different than P hat. Okay. How do we find the standard deviation of a mean? Much different than the standard deviation of a proportion, but the process is going to be the same. Okay. We're going to, instead of using a z-test statistic, however, we are going to use a t-test statistic. Okay, so we are going to be looking at t distributions rather than z distributions. For a t distribution, what's really important is degrees of freedom, n-1 degrees of freedom. We will always use n-1 degrees of freedom. We'll look at why that's the case at a later date. Right now, we just have to know, how does this t distribution work? Okay. Super important that we find the degrees of freedom, because we will not be able to use the table to answer these questions if we don't know what the degrees of freedom are. So let's jump right in and look at an example. Suppose you want to perform the test that mu equals 5 versus the alternative that mu does not equal 5 at the 0.01 significance level. A random sample of size n equals 37 from the population of interest yields X bar 4.81 versus the standard deviation of 0.365. Assume that all the conditions are met. Okay. Explain why the sample result gives some evidence for the alternative hypothesis. Why does this give some evidence for the alternative? Because it's not 5. Calculate the standardized test statistic and the p-value. Okay, so our t-test statistic, t equals the sample mean minus the hypothesized mean over, well, how do we find the standard deviation of X bar? Or how do we find that standard deviation? Well, it's just the standard deviation divided by the square root of n, like we saw on the standard error of the confidence interval last unit. So first we're asked to calculate this. Well, what was the sample mean X bar? Oh, X bar was 4.81 minus the hypothesized mean, which was 5, divided by the standard deviation of the sample, 0.365, divided by the square root of n. So I calculate this t-test statistic, and I get a value for this of negative 3.17. Now, when we're using a t-test statistic, we're always going to look at the absolute value. Now, we have a new table that we haven't met yet. Oh, no, we did meet this table in confidence intervals. So I have a t-test statistic of negative 3.17 with 36 degrees of freedom. Okay, so let's look here. Negative 3.17 at 36 degrees of freedom. So 36 degrees of freedom. I don't have 36 on this table. So remember, we always go to the next smallest value, 30. Now I'm going to look for this test statistic of 3.17. Where is 3.17? Oh, it's right here. So I go up to the top and I see that my p-value is greater than 0.001, but less than 0.0025. So I can find a range of my p-values. My p-value is in between 0.001 and 0.0025. So I can't find the exact p-value, but I know that it's greater than 0.01 and smaller than 0.025. Oh, that's a pretty small p-value, somewhere between 0.01 and 0.025. Therefore, this data would be statistically significant at the 5% alpha level. Let's use our calculator to do this test statistic and p-value. Okay, well, what kind of test are we going to run here? Remember our favorite button, stat, test. What kind of test is this? Oh, this is a t-test. Enter. Okay. Do I have data in the list? No, I have statistics, so I like that. What's my null? Oh, we think 5. What is my sample mean? Oh, that was 4.81. What was the standard deviation? Oh, that was 0.365. How big was my sample? 37. What was my alternative? My alternative versus the alternative of not equal to. So it was a two-sided alternative, and then I'm going to calculate. Oh, my t-test statistic was negative 3.166. My p-value was 0.003. That matches what we found here by hand. So this is a very small p-value. Therefore, the data is statistically significant, and we would reject the null. They didn't ask us to go that far yet, but that's what we're going to be doing with this. All right. So same process as before, but now we're using a different table if we find the p-value by hand. The level of dissolved oxygen. Let's do another example here. In a stream or a river is an important indicator of its ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along the stream. Sorry, guys. Here are the results in milligrams per liter. Do the data provide convincing evidence at the 5% level that the aquatic life in this stream is at risk? Okay, so what are they asking us to do? Find the test statistic and the p-value. If the p-value is less than the alpha level, then we think, yep, something's wrong. If the p-value is not less than the alpha level, then we're going to say, no, the aquatic life should be fine here. Okay, so let's do our 4-step process. Okay, what do I want to do? Mu is the mean, the true mean dissolved oxygen in this stream. What's the null? The mu equals 5. Versus the alternative, what are we worried about? That the oxygen level is too low, meaning less than 5. Okay. Are we allowed to do this? Okay. So step 2, SRS, they told us. Independence. How do we test independence? Oh, we would have to assume that there are more than 150 spots to gather water. Yeah, I'm sure there's more. Than 150 sample spots. All right. Did they tell me that the population is normal? No. Is n large enough to use the central limit theorem? No. Uh-oh. So how am I going to check normality if I can't use the central limit theorem? This is where we're going to have to go put all the data into a list and make a graph. If the graph is roughly symmetrical with no outliers, then we're okay. Well, how are we going to do that? Remember, if we go to stat, edit, and we're going to put some data in our lists. Unfortunately, I did not pre-do this for you guys. 4.53, 5.04, 3.29, and I'm just going to go type all these in. Okay, 5.23, 4.13, 5.5, 4.83, 4.4, 5.42. Now remember, you only have to do this if n is not large enough to use the central limit theorem and they don't tell us that the population is known to be normal. Then we have to check it ourselves for normality by making a graph. I personally prefer a box plot. However, you could use a histogram. Oh, really? What mistake did I make? Okay, let's look here. 4.01, 4.66, 2.87, 5.73, and 5.55. I messed up somewhere because you can see, oh no, I'll be okay. The last one was 5.55. Enter. So you can see that I have the right amount of data because 5.5 is highlighted and it's telling me that that is the 15th data point. And they told me here, there's 15 randomly chosen locations. So I know I have the right amount. Now remember, to make a graph, we're going to go to stat plot. Second, y equals. Stat plot 1 is turned on. I want to make a box plot. I want to make a modified box plot so it'll show me if there are any outliers. So I hit enter and it says, where did I put the data? Oh, I put it in list 1. Never, ever, ever mess with frequency. And then we tell it to graph. I don't see anything. Remember our favorite one, stat zoom, zoom 9, zoom stat. And it should give me, why is it not? Oh, I bet I have something in y equals. If this happens, make sure that you clear out your y equals. You see how this line y equals 0 was turned on. So it was trying to graph a line and a box plot at the same time. It's just too much for the calculator. So I'll tell it to graph again. I still don't see anything. Let's go to my zoom stat. What in the world? I made another mistake. That tells me that one of the points is way far away from the others. Oh, because this point number 1, I typed it in as 453 instead of 4.53. So you can see that if you make a mistake like that, you'll be able to tell on the graph, like, uh-oh, something's not right. Let's try graphing it now. Still doesn't look right. We'll use our favorite zoom 9. Oh, there's my box plot. Since there are no dots, there are no outliers. And it looks roughly symmetrical. So yes, whew, that was a lot of work, but we got to go through it to determine normality. So I could just draw a quick sketch of this. Since there's no outliers and it's roughly symmetrical, the data is approximately normal. All right, let's calculate our t-test statistic. Well, check this out. On the calculator, since I have the data in a list, I can come here and go to my favorite stat button. So I'm going to go to stat. Oh, I want to run a test. I want to run a t-test. I don't have the statistics, but I do have the data. And the calculator is going to say, okay, cool. What's the null? Oh, the null is 5. Where did you put the data? List 1. Never, ever, ever mess with frequency. Okay. The alternative, oh, I want to test less than. Calculate. I have a t-test statistic of negative 0.94 and a p-value of 0.18. So negative 0.94 and 0.18. Negative 0.94 and a p-value of 0.18. Since the p-value is greater than the alpha level, I fail to reject. Okay. So the data is not statistically significant. We fail to reject the null. We do not have enough evidence to conclude that there is less than 5%. Okay. So overall, what are we saying? We do not have enough evidence that the true mean level is less than 5% in the string. We fail to reject. We do not have enough evidence to conclude that DO is less than 5. All right. Now, that was part A. All right. We ran the 4-step process. What are we going to do? Are we allowed to do it? Do it. Tell us what it means. Okay. Then let's look at question B. I'm going to have to erase all this just so we have enough space to work through this second part of the problem here. Given your conclusion in part A, which kind of mistake, type 1 or type 2 error, could you have made? Explain what this mistake would mean in context. Well, we failed to reject the null. So if we fail to reject the null, we could have made a type 2 error. Well, what is a type 2 error? We fail to reject when in fact it is false. Okay. So remember that our null in this case was mu equals 5 versus our alternative that mu was not equal to 5. Except I wrote the wrong alternative because it was less than. So that's why I'm confusing myself. All right, so let's go back and start this again. Type 2, we fail to reject. That means we're saying that it equals 5 when in fact it is less than 5. If it is less than 5, it will not support aquatic life. So in this case, we would have made a type 2 error. We fail to reject. So we say that the mean dissolved oxygen level is equal to 5 when in fact it is less than 5. Therefore, we say, yeah, this stream's healthy. It can support aquatic life when in fact it could